superimposed, like of the participants. Yeah. Okay, so I think we can probably start. So maybe more people come in on the way, but if they're late, they're late, you know. Yeah. So it's our pleasure to have this semester's last ITAMP seminar, a special seminar because it's online. And it's our pleasure to have Rick van Bijnen with us. And so Rick did his PhD in 2013 at the University of Eindhoven. And in this context, I would like to point out that it's actually like he wrote one of the theses I wrote, or like I read most, or also as the first when I was beginning as a grad student, called Quantum Engineering with Ultra-Cold Atoms. And it's like very pedagogically written. And I recommend it to anyone who starts in the field of Rydberg atoms. And that was also Rydberg atoms and their interactions. And so he continued in this field also in Dresden during a postdoc with Thomas Pohl, before he left Germany again for Austria this time. And ever since, he's been in the group of Peter Zoller in Innsbruck. And so today, Rick will be telling us something about entanglement, Hamiltonian tomography, and quantum simulation. So the screen is yours.
The screen is mine. Okay, thank you very much, Valentin, for inviting me to talk about our work on entanglement, Hamiltonian tomography, in quantum simulation. This is a work we did here in Innsbruck, and I just point out first here that the main PhD student who did all the hard work here is Christian Kokal, who is actually also in the meeting. So just want to point this out. So what is this about? So first, quantum simulation, I don't really have to introduce it, I guess, but this is one of my standard slides that I've been using for years, and sort of tradition to have it here. Let's say you have some complicated spin system or some material that you want to calculate something. You know, you can model this as a spin Hamiltonian, but as we know, for a quantum system, this doesn't fit in your computer, and rather what you can do is maybe build something in the lab, you know, maybe with ultra-cold atoms that mimics this target system here. And then rather than calculating your answers, you can just measure them in a controlled environment. So this idea has been around for a while, and in the last 10, 20 years, some very impressive results have been obtained. Like there's a large variety of systems, also like ultra-cold atoms and optical lattices, Rydberg atoms, also trapped ions and things like this. And here the experiments have become quite impressive, and one of the key features here nowadays is that we have really single particle control, and we can also measure the state of single particles. Like this is something that's unthinkable in a real material, obviously, but this now allows for a quite unique window of the quantum world. Right, so with these platforms, we can now really study quantum matter at the single particle level. And obviously what makes these systems interesting, you know, what is interesting about quantum matter is entanglement, right? So these particles, they're all correlated with each other. And the way to study and quantify entanglement is usually that you divide your system into a subsystem A, a subsystem B. You can write down then a reduced density matrix for system A. And this density matrix, it will be mixed because you have been cutting some of the links to the environment, to the remainder of the system. So this density matrix here will be a mixed state. And the rank of this density matrix tells you more or less how entangled this subsystem A was with the subsystem B. And one sort of one way of writing this density matrix, or which will hopefully provide some intuition, is you can write this row A. This is an operator, a matrix. I can write this as the exponential of some Hamiltonian. And this quantity here is called the entanglement Hamiltonian. I will go into more detail later, or can also maybe give one little piece of intuition here. Like if I pull out sort of like an overall scaling factor out of this entanglement Hamiltonian, you see this kind of looks like a Gibbs ensemble. And this beta is sort of an inverse entanglement temperature, is what people call it. So if this beta is very large, right, then the entanglement temperature is very low, and you will find that this thing just reduces to, or this density matrix here just reduces to a single or a rank 1 matrix, so just as one component, and it's not entangled with the rest. So this is a product state. If beta is very small, I always have to think, right, then I have a very high entanglement temperature, and this turns into an identity matrix. So it's really maximally entangled with the environment. And this entanglement Hamiltonian is sort of like the focus of this talk. What we will do is entanglement Hamiltonian tomography. You can read this. This is also the title of the talk, and you can read this basically 2 ways. So one way is I can do tomography of the entanglement Hamiltonian. So we try to determine this thing out of experimental data. And the other way you can read it is that we do tomography of a quantum system using the entanglement Hamiltonian. So both interpretations fit basically to this talk. So this brings me to the outline of the talk. So first I will explain a little bit more the entanglement Hamiltonian and the entanglement spectrum. Then I will continue with doing the tomography that I just talked. Give some more details on why it works the way we do it, how we can verify our answers, show a few more examples, and then reach hopefully the conclusions without going too much over time. So there's 2 things, the entanglement spectrum and entanglement Hamiltonian. I want to make a bit more precise here. So let's say we have a quantum many-body system. This is a closed system, so there's just a single wave function, a pure state, like you would obtain maybe in an experiment where you find ground states or where you do quench dynamics. And now we split this system into 2. So in a subsystem A and a subsystem B. And then what I can do is I can write down a Schmidt decomposition of this state. This is something I can always do. I can always find a basis for subsystem A and a basis for subsystem B, such that I can write this global wave function in this way. So, and the number of components I have here, like the number of non-zero product states here, this tells you how entangled my state was. So if I have only 1 here, that means that this entire system was just in a product state of this phi alpha or phi 1 for subsystem 1 A and phi 1 for subsystem B. So it's a product state. But if I have more, it means it was an entangled state. So then the rank, or basically if I now calculate the reduced density matrix, so I trace out subsystem B, then I find something of this form, and we see here exactly these Schmidt components. So these state factors here, they appear here with some prefactors. And then the number of non-zero components here, that's the rank of the density matrix, and this tells you how entangled it was. And then here, okay, like I said already before, we can write this density matrix in terms of an entanglement Hamiltonian. And then let's say the amplitude of each of the Schmidt components is actually, it's given by the energies of this entanglement Hamiltonian exponentiated. So this is called the entanglement spectrum, sort of the eigenvalues of the density matrix. Right, so that's just to make the connection. This value here is this lambda alpha squared. And here again, we see this entanglement temperature. So maybe here I can be a bit more precise, right? So if I make this beta very large, right, then all the energy gaps in this entanglement Hamiltonian blow up. And you see here that this, with all these exponential terms here, just one of them will be significantly non-zero, and the rest will be exponentially small compared to it. So if I have a very large beta, which meant I had 0 entanglement temperature, you see I only have here 1 Schmidt component that's relevant, and I had a product state. And in the other case, when I make this 0, then I just get here all components have the same weight. So I have a very entangled state.
Can I ask a quick question here, Rick?
Yes.
Is this assuming the reduced density matrix is diagonal necessarily, or like row A?
No. It's not diagonal. So, well, yeah.
It's diagonal in the basis of phi alpha A.
No, but this is still a matrix.
Okay.
This thing. So if I just take here a state vector and I mean, it depends on your basis, right? I can find
okay.
Yeah. But if I just take a random, like a basis somewhere, then this is still a matrix.
Okay, great, thanks.
Maybe a follow-up on the, are the phi A's, are they orthogonal?
Yes, this is an orthogonal basis within the subsystem A.
Okay, but
each of them has a unique counterpart in subsystem B.
But then in the spaces or in the space A, like, wouldn't this matrix then be diagonal? I mean, in this.
Yeah, in this basis, yes.
Yeah. Okay.
So I can pick a basis, yeah. But usually, you know, this means you really have to diagonalize this thing and find everything. So if you're just working the basis, it usually just looks like a matrix, and you cannot tell what the rank is. Like, you have to do a single value decomposition and analyze it really. Like, this is sort of the statement. Okay, so why is this useful, right? Why are these things interesting? There's entanglement spectrum and there's entanglement Hamiltonian. So, like, if I could measure this, if I could find this out from an experiment, obviously I can compute all entanglement, or not all, but a lot of entanglement measures, like the von Neumann entropy or the Ring entropy. So you get a lot of information out in a way. Turns out also that this entanglement spectrum can be a sort of a diagnostic tool for if you are studying topological phases, that it will tell you something about the edge modes and things like this. I will go in a little bit more detail in a minute. You can see quantum phase transitions in the entanglement spectrum, which we will also see later. And maybe as a sort of side remark, it's very hard to obtain these quantities numerically. So a lot of people are interested in the entanglement spectrum, especially in the context of these topological phases. So many papers on topology now always analyze the entanglement spectrum, but they have a hard time calculating this. And this is also why we are now interested in measuring this thing in quantum simulation. So I'll give a small example on the relation between the entanglement spectrum and topology. So let's have a look at the ground state of the AKLT model. The AKLT model is a spin-1 chain here with a certain Hamiltonian. And exactly for these parameters of this Hamiltonian, this model has a ground state which has a very nice interpretation. So you can view the ground state of the spin-1 chain as if I had spin-1 halves, two spin-1 halves at each side. And then you consider basically the triplet subspace. So let's say I can imagine this also as if this was a spin-1 half chain, twice as many spin-1 halves, but I put a large penalty on singlet states at each pair of spins. So I have here triplet states, and then every time the neighboring spin-1 halves here between two of these sides, they are connected in a singlet state. So in this ground state here in the end, you see, I mean, all these spin-1 halves, they are paired up together, except the outer ones. They are free, they have no partner. And these are then, these give rise to a fourfold degeneracy of the ground state. So I always have this valence bond ground state, and then the edges are free. So I always find, in this case, 4 ground states where I can make free edge excitations. And what happens now if I cut this system in two, then you also find, basically, you cut here a singlet, and then I find in the entanglement spectrum, I find only 2 Schmidt components, which are, again, one of these valence bond states. But now, again, I create here a spin up or a spin down in these 2 Schmidt components. So you kind of see the same edge physics as you saw for the entire state, you see this back in the entanglement spectrum. So the Schmidt components, they kind of reflect the topology of this state. Okay, and this is a very simple example. Right now I have a 1D system. I cut it, I get 2 levels out in the entanglement spectrum, but this works also in higher dimensions in 2D, or like if I make a cut here and I look at the or I take a subsystem and I look at the reduced density matrix, then again, you see in the entanglement spectrum, you see exactly the edge mode physics. So this is called the Lee-Haldane conjecture, that this entanglement spectrum is sort of related to the spectrum of edge excitation. It doesn't matter what shape I cut out here. And this was a big thing. This is a PRL from 2008. And this is what got many people interested in the entanglement spectrum. Okay, so now our question is basically, can we measure this entanglement spectrum? So this brings me to the second part here, right? So how can we do tomography of this entanglement spectrum and the entanglement Hamiltonian? So have a look at, or if you want to find, or if you want to do tomography of a quantum system, I will look at one particular flavor of this. It's tomography with randomized measurements. So let's say we have here our quantum system in the lab. So I have some ions, I do maybe a quench, prepare some state here, and then I look at the subsystem. What we do now is at each site, this is a spin system, right? At each site I apply some random single particle rotations, and then I measure. And then if I measure, I get here I measure in the Z basis, I always get either a 1 or a 0 out if I had spin 1/2 states. So I measure here bit strings all the time. This way I collect now a lot of bit strings, right? So let's call these bit strings S, right? So I collect a lot of data every time in a different random basis. Okay, so here in notations may be a bit confusing, but this U is now a collection of random unitaries. So every time I rotate my spins randomly, I collect a lot of statistics in this basis, like which bit strings did I see. So each bit string has a probability P under a given rotation U of finding this bit string S. And then what you can basically classify most tomography methods as in the following way, that you just take this data here, and then you try to fit some parameterized Ansatz for your density matrix rho with some parameters X to the data you collected, it's PU of S. So a famous example is, it's called low rank least squares. So I just take as parameters, I take a rectangular matrix with some rank chi, because usually the states that you get here are not full rank, so they may be low rank. So I can take a low rank Ansatz and construct out of this positive semi-definite matrix, which the density matrix has to be. And then we just try to collect enough data so that we can fit all the entries of X. But this X is a exponentially large matrix. This D is the Hilbert space dimension of your system, of your subsystem. So this is an exponential procedure. I need exponentially many samples here in order to be able to determine all the entries of X. Another famous example is called projected least squares. And that is sort of, you take all these bit strings and all these histograms here, and you can calculate exactly which matrix would have produced these answers. The problem here is that this is not a physical matrix, like it's not a real density matrix. It can have negative entries on the diagonal and the trace can be not 1, but then you can project it back onto the space of physical density matrix. It's called projected least squares. So what we do here today is we try something else. I mean, this projected least squares is also still in principle exponentially scaling. And what we do here today is, okay, you could have guessed this by now, maybe, that we parameterize our density matrix Ansatz using some entanglement Hamiltonian. So we take here an Hamiltonian with parameters, and we use this as an Ansatz for our density matrix. And now we try to fit these parameters X from the data.
Can I just maybe ask you, like, quickly, what's the purpose of the random unitaries? Why do you need them?
you need to measure in different bases. Maybe that's the simplest or the most straightforward. If I would not do random unitaries and I just measure in the Z basis, then I only collect information for the diagonal of the density matrix. Right, in this Z basis, I can only then fill out, or I can only fit entries on the diagonal. I have zero information about the off diagonals. If I want to obtain information about the off diagonals, I have to measure in a different basis.
Right, but the randomness is like for every measurement you have a different unitary. No, like it's one random set of unitaries, and then you measure all the bit strings in that with these unitaries.
Okay, well, you can, for one set of random unitaries, I can collect basically a bunch of bit strings. You can decide beforehand. There's actually this projected least squares. Actually, in this recent Nature Physics paper, they do something that they call shadow tomography. That's actually the limit case of the projected least squares, where I just take one shot in each basis. And they show that for certain purposes, this is actually optimal. Just do one shot in a random basis, so I get one bit string, and then I move on to the next basis. But in principle, you can also say, okay, with each basis, I do 100 shots or 1,000 shots to really collect a histogram, right? Because in this one shot, I just get all entries in the histogram as 0, and except one peak is 1, right? That's the. Okay.
In this Ansatz here, is the X parameterization any simpler than the having like exponentially large Hilbert space in the previous Ansatz? And then because if it's very large, then if you take the exponential, it gets even more complicated. So where are you winning in this Ansatz?
Yes. So this is the perfect question. This is exactly what I was going to say, right? So how do you now gain by this? And this is just a reparameterization, except with this additional step in between that I have to exponentiate this thing. But in principle, yes, these should be as many parameters as I had degrees of freedom in here, right? So I don't gain anything yet. But I mean, because in principle, this entanglement Hamiltonian can be highly non-local and include many body terms, right? That's sort of what you would say then. And I still have a lot of parameters. But as it turns out, actually, right, so what should we now put in here, right? Obviously, if I just put an arbitrary matrix here, I don't gain anything, as you ask. But we can put something smarter in here. And I will just skip right through our recipe that we found, like what works. And then I will go into the details of why it works and how it works. So basically, we have 3 ingredients in this entanglement Hamiltonian. So the first is we just put the original system Hamiltonian in. So if we were studying a ground state, or if we were studying Quench Dynamics, we just take this Hamiltonian. Let's say if this Hamiltonian was H and it's made up a sum of other operators, HI, I can always write it like this. Then we just take as our, let's say the first level of our Ansatz, we just take the same operators, but we just give each of them a constant in front, right? This is then a fit parameter, right? So if this was a normal lattice model, you know, where I maybe have nearest neighbor interactions and local fields, I get here order n parameters instead of 2 to the n. The second thing we do is we include momentum terms. So you can sort of argue that if I take commutators, if these are somehow localized operators, they're localized on sites I can sort of make momentum-like terms out of commutators of these terms. And we just add these again to our Ansatz. And again, I add a constant in front. That's another fit parameter I have. And then finally, this is another thing we needed, is we can add k local corrections. So where k is typically much smaller than the subsystem size. So just add here 2 body operators, 3 body operators, etc. K is maybe 2, 3, 4, something like this. And I can again add fit parameters in front. So this is the recipe. I will go in details more, but let's first just try it. Let's go to the lab here. This is the lab here in Innsbruck. It's in the basement below me, where they have trapped ions, where they can make 10, 20, and nowadays even 50 ions in a row and trap them. And on these ions, they can realize Ising-like models. So this is called a long-range Ising model. So I have an XX interaction with some Jij in front, which is with a power law. So it's decaying with distance, but it can be actually a slow decay. And then also they can do local fields. And on this experiment, they can now, for instance, like just apply this Hamiltonian for some time to do a quench, or they can maybe do some single particle rotations. Yeah, so we will go now like some data that they took by just applying this Hamiltonian for some time and then doing the randomized measurements. So they collected a lot of data on this system. And we will see, how well can we fit our parametrized ansatz with the entanglement Hamiltonian to this data. So here we have the Quench Dynamics, and actually what we want to see now is the entanglement spectrum. Right? So if I do this Quench Dynamics and I look at the reduced density matrix, we can actually do theory calculations here. So this is for a subsystem of 5 ions out of 10. You can simulate this. You can calculate the reduced density matrix, and then you see this entanglement spectrum. So at time equals 0, we start with a product state. So we put all the particles in some definite state. So we see I have only one non-zero eigenvalue in the entanglement spectrum. And then as soon as time begins to run, right, we apply this Hamiltonian, these particles start to get entangled, and we see more and more Schmidt components becoming non-zero. So we see here basically the growth of entanglement in this experiment. Right, so this is a theory calculation. So the orange bands are a simulation of our entanglement Hamiltonian protocol, but actually we have data and we can really apply our protocol, and we can compute the Schmidt spectrum from the data by fitting our entanglement Hamiltonian ansatz. And then we get here these points out. And then you see really like they match quite well with the theory. So this is sort of like you can see the Schmidt spectrum here growing live in the data. You can really follow the entanglement growth in there. Okay, this is let me just quickly say these are at different times, like t equals 0, 1, 2, 3, 4, 5, or like 2, 3, 4, 5. I can look at the Schmidt components and see how well we get a match, and you think, okay, maybe here it doesn't look so great, but these are all the xi of us, which are the the actual eigenvalues are the exponential of these values. So actually here the values are already pretty big, so it means it's like the small stuff down here that you see, so it gets blown up here in this view. One thing we can compute here, for instance, is now the von Neumann entropy. I don't think this has ever been measured so directly before. So here's our prediction for the von Neumann entropy, or the solid line is what you calculate from theory, and here is what we get out from our procedure. So again, you see the von Neumann entropy growing in time. So you see the entanglement basically growing in time in this experiment. Right, so this was tomography of the entanglement spectrum using the entanglement Hamiltonian. Right, I just gave it now as a recipe without explaining why. So I will briefly give a bit more motivation of why we take these ingredients here. So first, the deformed system Hamiltonian. So one argument for this is just thermalization. So it's well known that in many systems, when you do this quench dynamics, and I do this for a long time, then we know that eventually this subsystem sort of thermalizes to a Gibbs ensemble. And here the HA is really the system Hamiltonian on this reduced subsystem. So it's this guy here that we've been applying for a long time. So and then if I look at this, we see, okay, our entanglement Hamiltonian apparently is of the same form as the system Hamiltonian. So that's one argument why we should take, well, not even a deformed system Hamiltonian, but maybe just the system Hamiltonian itself already. But I have more arguments for why it should be deformed. Namely, there's another theorem from axiomatic quantum field theory. It's called the Bisognano-Wichmann theorem. Okay, this is defined for continuum systems with Lorentz invariance, where you have not a Hamiltonian but a Hamiltonian density, basically. And it's known, or at least Mr. Bisognano and Wichmann have shown in the 70s, that if I cut the system into two halves, this is an infinite system, I cut it somewhere, they actually managed to calculate the entanglement Hamiltonian exactly, or the reduced density matrix exactly. And it is of this form. It's basically, again, your original Hamiltonian, but with a spatially varying entanglement temperature in front. So, and it turns out, I mean, this is now derived infinite systems in continuum, etc. But it's actually people like, for instance, Marcello Del Monte did a lot of this. He looked at this also, does this also apply to finite lattice systems? And the answer is yes. In many cases, this actually also works. So this suggests immediately for us, for our entanglement Hamiltonian, that we can try this deformed system Hamiltonian. Right, so we saw the first part, the deformed system Hamiltonian, is suggested by thermalization, suggested by this Bisognano-Wichmann theorem. Then the momentum terms, the second ingredient. This we took from, we took our inspiration from conformal field theory, which is basically quantum field theory at a critical point. There, people, like in these papers here below, they managed, like, don't look at this expression too seriously, but they managed to derive exact expressions, at least under certain conditions, exact expressions for the entanglement Hamiltonian, with some impressive looking prefactors. Again, expressed in terms of the original Hamiltonian itself, with maybe some spatially varying prefactor and so-called momentum terms. And you can do, this is again in a continuum, I can do this in a lattice. And these momentum terms then look like what I showed before, like commutators of parts of the Hamiltonian. So they were able to show that you can find an exact expression, which is again basically spatially deformed system Hamiltonian. Where is it? There is it. Times a momentum term with a spatially dependent prefactor. So we can say, okay, in certain circumstances, we know it has to be like this, that these extra momentum terms should probably also be added. Then finally, the k-local corrections. Well, actually, to be honest, this is more like we just hope that it works, or like if you sort of take a systematic continuation of these two, okay, you can start adding more terms, but you add first small corrections and make them systematically bigger. Okay, this doesn't sound very convincing, obviously. Like you might now wonder, yeah, what is he telling us, right? Just pray and hope for the best. So, you know, when I show these things, how do you know that these answers that we get here, that they are correct, right? So there's no guarantee for this. So this brings me to the next topic, verification. So how can we tell, you know, what we are doing all here? How can we tell that this is actually correct? And for this, we use another protocol that was developed here in Institut by Andreas Elben, who was a PhD student there at the time, is now a postdoc here. He developed a protocol where we can compare two platforms. Let's say you have two quantum computers or quantum simulation platforms, and I want to see the states, row 1 on one platform, row 2 on the other. How well do they overlap? What's the sort of the fidelity between them? And he did this with randomized measurements. So we take again a randomized data set on platform 1. We take another data set on the other platform. We collect a bunch of histograms there, and then we correlate these answers. So we developed some formulas of doing this, so how I can compute basically the overlap between these states from this data from platform 1 and data on platform 2. But now, obviously, we have only one platform, right? So we have our platform 1, which are the ions, where we took data. So what we do now is we split this data set into two. So one half of the data set I use for computing my entanglement Hamiltonian. or fitting or doing our entanglement Hamiltonian tomography, determining the parameters. This now gives me a density matrix on my computer in this case. So I have here this thing, and then I will compare the fidelity of predictions from this one with the remaining data from the ion platform. Right, we have to split it like this. We cannot do compare this one with the data that we fitted it from, right? Because you end up with a sort of self-fulfilling prophecy. So that's why we split it. We fit from one data set and compare to independently taken remaining data. So we can do this for our ions that I just showed you before, where we experimentally determined the entanglement spectrum. So this is 10 ions with subsystem 5 out of 10, and here's 20 ion data with 5 particles in the middle. And we can compute the fidelity if we just take the deformed system Hamiltonian as an ansatz, for instance. And then we see, okay, in the beginning, when it's a product state, we get a high fidelity, close to 1, but afterwards it's not so great, right? So it's 30–40%. So we know that this is not enough here. So you can sort of systematically check now whether your ansatz was right or not. For the 20 ion data, it's also not so great. So now we can add, for instance, momentum terms, the ones that I discussed before. So now to our ansatz, we have this system Hamiltonian, but we also add terms of this form. These are the ones that you would compute if you from the Hamiltonian of the ions. And then we see, this already improves, right? So now we get about 80%, 80, 70, something like this. So it's still maybe not a great fidelity, but at least you see already the majority of the physics is captured by just an entanglement Hamiltonian with just these terms. So then we can add our higher order k-local terms, and systematically we can keep improving our ansatz. Every time we can check from this cross-platform verification protocol, we can compute the fidelity, and we know really how well we are fitting this thing. So we know how well it works, how correct it is.
Excuse me?
Yes?
Do you know why the prediction worked better in the left-hand system than on the right-hand system?
Well, it's just a bigger system, and it's an experiment. It's just a bit more messy. There's a bit more decoherence, right? They have twice as many chances of something decohering. And already you see it here in the initial state, right? So it's really, this is a product state, but already there the fidelity is only 80%. Actually, if they look, the initial state is a antiferromagnetic, so they prepare an antiferromagnetic state. And if they just prepare this state and then measure again, they're already somewhere between 80–90%. So they already lose a bit of fidelity there. So it's a bit more messy.
Is there any intuition for, I guess, to follow up on that question, on the right, it was a better prediction when you only had the first term. It was higher fidelity, even though they were both pretty bad. And then as you added more and more terms, the improvement for the smaller system with only the 5 atoms on one end, that had much higher improvement than the larger system with the 5 atoms in the middle, right? And is the difference in improvement just a system size thing, or does it matter where you pick your subset of atoms? Does it matter whether they're on the end or in the middle?
This I don't know. Maybe Christian, if he didn't fall asleep yet, maybe he can comment here. He tried many different things. Is there anything specific you can say about this?
So I know that for the 10 ions, this is this plot on the left. There, the fidelity, the situation looks similar, independent of where you pick the subsystem. For this 20 ion data, I would really have liked to pick a subsystem on the boundary, but unfortunately, we don't have data for the boundary ions for this 20 ion system. So our experimentalists did the quench here for this 20 ion chain, but they only applied these random unitaries to 10 ions out of the center. So unfortunately for these 20 ions, we don't have data for the boundaries.
I see. That's helpful to know. Could one of you also comment on like what's the highest degree connectivity K that's feasible for these many body terms? I think you're at 3 right now. Is that the limit of being able to extract a model, or could you do degree 4 connectivity or even higher?
So what? Obviously, like the higher I make here the K, of course, the more terms I get. So I have more parameters to fit. So in principle, the theoretical fidelity that I could attain, obviously I have a more flexible model, right? So it should become higher. But on the other hand, I also need more data, right? The more parameters I get, the more data. So actually what I would do here is not just increase K blindly and just give a free parameter for each term, but maybe, you know, if you shape this a bit, that at least the terms where the particles are next to each other or nearby, that you somehow make these larger, and the ones which are really far apart and not really connected, that I give this a smaller amplitude. So that I add maybe some function of KLM here in order to reduce the number of parameters. Because I mean, if I start, okay, here it's 5, right? So if 4, there's not so many, but if I would do this for 10 particles, a subsystem of 10, I really introduce many extra parameters, right? So it's still polynomial, but yeah, it's a big polynomial. So.
Okay, great, thanks.
Okay, so we saw entanglement, Hamiltonian tomography, some arguments why we should make these local ansatzes for this thing, that we can actually check this. And many of these motivations, not many, but these motivations, they came from, for instance, conformal field theory. So actually we can now go maybe to, let's say, a situation where we know that the CFT, conformal field theory, kind of applies, and see how well it works there. Just as a method of benchmarking our method a little bit, and also as a future applications, right? So if you are now having a system in your lab where you think CFT doesn't directly apply, or I'm not sure, or you want to know, is this CFT really correct? You know, then actually, if you do entanglement tomography, you can either confirm or falsify predictions from these theories. So it's multiple reasons that's interesting to look at this. So what we do is we do now quench dynamics with our long-range Ising model. So this is the model realized by the ions, and we can quench to a critical point of this model. So what we do is we start again with a simple initial state, maybe a product state, and I just apply a quench. So I start evolving with this Hamiltonian. So again, so here we have our system. So I just put here space in the vertical direction and time in the horizontal. I partition it in a subsystem A and B. And now at time t equals 0, right? So this quench, I can sort of view this initial state, psi 0, now actually as the ground state of the Hamiltonian plus a bunch of quasi-particles, right? So this was not an eigenstate, but I can sort of write it in terms of the eigenstate plus extra stuff, quasi-particles. So what will happen is that these quasi-particles, as time moves on, these will start to propagate in the system. So let's say I have here, at this point, I created 2 quasi-particles which propagate away from each other. One of them enters the subsystem, and the other goes in the other direction. So now this is actually the mechanism that creates entanglement between these 2 systems. As time moves on, more and more of these pairs enter the subsystem and entangle it with a quasi-particle outside the subsystem. So you see this if you now look at the von Neumann entropy, so the measure of entanglement as a function of time. You see that in the beginning, we start with this almost product state. There's no entanglement. And as time moves on, the entropy increases up to a certain point. I mean, and this is just more and more pairs of quasi-particles entering the subsystem. But so at some point, we see actually that it saturates. And this is actually due to the fact that these quasi-particles also move out of the subsystem again. And at some point, you reach a balance. There's equally many quasi-particles going in and out. And the entanglement doesn't change anymore, so it's relatively quiet here. But then at a later time, we see actually that particles reflect on the far edge of the system. So this is for 20 particles, if I recall correctly. Actually, these quasi-particles, they reflect off the boundary and they come back in again here. And you see things happening again to the entanglement entropy. It gets a bit messy here. And okay, so this reference here, actually, this is a nice description of this quasi-particle mechanism that I sort of schematically explained here, but they do it a bit more thorough with nice pictures. So this is actually very good to read. So we can do now on the system, we do simulations here in this case. We can simulate our entanglement Hamiltonian tomography procedure. So now in this case, we take as an ansatz, we know it's CFT, so we take our deformed system Hamiltonian plus momentum terms, which were suggested by the CFT. And then we can do here the fidelity check. So how good is our reconstruction now of this density matrix? And you see here an orange line and a purple line. The orange line is without the momentum terms, and the purple blue line is with momentum terms. And you really see in the beginning, without momentum terms, the fidelity really drops. But then if I include the momentum terms, I see I get a really high fidelity again, close to 1. And this stays like this all the time until we reach this regime where the quasi-particles come back and it becomes messy again. So what this tells you, this means that if I now do our entanglement Hamiltonian procedure, by including or excluding terms, you can really check, what is now the operator content of this thing. We can now say, okay, in this way, you would have discovered, by analyzing this, you would have discovered that you need these momentum terms in this situation. Yes, sorry. And another thing we can do here is we can look, how well is this fidelity that we get versus the number of measurements that we needed. So with this simulation for the CFT quench, we did this analysis. So we plot here the infidelity, so the remaining error, as a function of the number of measurements. And the number of measurements is really the number of measurements times the number of unitaries for this randomized unitary. And we see here our entanglement Hamiltonian procedure, which decreases quite rapidly. And at some point it flattens out. And this means basically your ansatz, this remaining 0.5% here, or no, this is less maybe, this remaining error, this is just an error of the ansatz. So even if I measure more, I cannot really get a lower fidelity. And then we checked, for instance, for these other competing methods, or sort of like the most popular ones, low ranked least squares and projected least squares. We really see, that, well, they don't even get near, right? So to get this 1% fidelity, the low ranked least squares plateaus here, the projected least squares actually might ultimately reach it, like if I change some parameters here, but I might need 10 to the 8 or 10 to the 10 measurements compared to our entanglement Hamiltonian, which reach a 1% level at maybe 1,000 measurements in total, which is very, very few for tomography of 5 sites here. And if we do larger subsystems, we can go up to 8 or 10. This picture stays like this. Entanglement Hamiltonian is super efficient and the other ones are not. Okay, so the other thing we can check, so with the conformal field theory, you can also, for instance, now check this Bisognano-Wichmann theorem. Right, so we look at ground states of this long-range Ising model, and we can see in our experiment, right, so we take, again, our ansatz. Now it's ground state, so we just take the deformed system Hamiltonian, and we can simulate what we would see in the experiment. So if we simulate the full procedure with a finite number of measurements, then you would see here, like this model, actually, I forgot to say, this has a phase transition at B equals to 0.7-ish, somewhere here, where it goes from a paramagnet on one side, so this is a pure state, to so the product state, sorry, to an entangled state on the other side. And you see this in the entanglement spectrum. Like, this is really the orange ones. If we take a certain fixed budget, the orange lines are basically what our method would have predicted from this fixed budget. And you really see you would be able to detect this phase transition here. Also, if you then look at the coefficients that you fit, you would see indeed these spatial ramps predicted by the Bisognano-Wichmann theorem. So this would be a way of like discovering this in your experiment or verifying these predictions. And finally, again, for this situation, we did again a scaling analysis. Now really I do something slightly different. I look at a fixed fidelity. So I say, okay, I demand a 1% error. How many measurements do I need to get a 1% error for various subsystem sizes? And then you see that with these other methods, like projected least squares, low rank least squares, these are really scaling exponentially. Whereas our method, it's not entirely clear from this plot, but actually it flattens off. And we found later, when we were already submitting our paper, we found actually, or one of these authors actually pointed out to us, they actually were able to prove that this entanglement Hamiltonian can be fitted with a polynomial number of samples. Right, so it's really provably efficient in the sample complexity.
Maybe can I just interrupt and ask a quick question here?
Yeah.
So now this is about the ground states, right? Like you, is that somehow like the measurement procedure for ground state and quenches? How does that differ? Or
the measurement procedure, it's the same, right? It's just, I mean, in all of this, it's always, where's the slide? Right. I always make too many clicks in my slides. Oh, come on. Right. So it's always like this, right? So we do randomized measurements on the subsystem of some pure state. And this can be anything, right, that you prepare. In one case, we prepare a ground state. In the other, we look at quench dynamics, right? So, but the following principle is then always the same. So there's always some pure state that you prepare, and on this pure state, I do these measurements on the subsystem, and I try to determine the entanglement Hamiltonian.
Okay.
Does that answer what?
Sure, but okay. So, but you kind of like, you have to know the ground state in advance, and then you kind of like prepare it?
Oh, yeah. I mean, that's a separate problem, right? So how you get this ground state there? Maybe you do some adiabatic state preparation, or you do something else, some variational procedure, right? That sort of, this is just saying, given that you prepared a state you want to analyze, for instance, a ground state that you think you prepared in your experiment and you want to analyze it, and then we come in. So how you get to this state, that's sort of not the focus here, let's say at the moment.
Right. Fair enough. Cool. Thanks.
Yep. Okay, so we saw, right, also that the scaling is actually quite good, right? So this is a very efficient method. Okay, so this brings me to the conclusions and the outlook. So we discussed entanglement Hamiltonian tomography. So either tomography of the entanglement Hamiltonian or tomography using the entanglement Hamiltonian. Both views apply. Where we took a physically inspired Ansatz for this entanglement Hamiltonian. And we can, with a low number of parameters, and this we can sort of fit efficiently. This allowed for the extraction of entanglement properties actually from real experimental data, right? So we were really able to measure the entanglement spectrum as a function of time. You see the growth of entanglement, you can see the von Neumann entropy. This Ansatz, you can sort of, with our, let's call it recipe, you can build it up sort of systematically, but importantly, you can also verify at each step. And this way, this also provides really like a method for testing maybe, Bisognano-Wichmann or CFT predictions in actual experiments, right? Like we saw here. This is efficient in the number of measurements that we need. But actually, this is somehow, I didn't say this, but actually it's not efficient in the classical computing effort, right? Because we have to form, when we do this procedure, we have to form this matrix. So we have to take this entanglement Hamiltonian and exponentiate it in order to sample from it and fit the parameters, right? And this is exponentially complex. We're looking at ways of avoiding this. Maybe you don't have to form it in order to give prediction from it and sample from it. But a very interesting other direction is actually to replace this sampling part with another quantum protocol. So maybe I prepare this state and sample from it, or we have some ideas of where we do time evolution with entanglement Hamiltonians. This is another project that's now in our group being prepared, like a draft is slowly being written these days. It's by Bhuvanesh Chanda, and also Christian is one of the main authors on this. Okay, so this brings me to the end. I just want to thank briefly, like the other people, obviously Christian here, who did most of the hard work, also Andreas Elben and Benoit Vermeersch, and obviously Peter Zoller. Were all very important in this work, and also I want to thank the ION people here, right, so that shared all their data and were always there for discussions and ideas. With that, I'd like to thank you for your attention.
Well, thank you, Rick, for this very nice talk, very pedagogical. So I encourage anyone to just like unmute and ask additional questions. I guess we had already a couple. So maybe I can start with like just a curiosity, like when you and not directly related to your own work, but like when you had this plot with the quasi particles going in and out of the system, why did the entanglement decrease when the quasi particles re-enter the system, like the top system? Like in the beginning, like it kind of like increased when they entered it, and then they kind of left and entered again, and then it just started decreasing. Is that some?
Okay, maybe bring up the plot.
Is that a recurrence?
Sorry?
Is that a recurrence?
A revival, you mean?
Sure.
Yes, this could obviously be, right. It's a finite system, so revivals, or at least partial revivals, are certainly possible. I don't know in detail what happens here. It's also here, it starts to work less nicely, so I always just classified this as a mess that we don't really want to look at. But maybe Christian can comment a bit more if you have any.
Yeah, I'm also not the expert on this, but I know that there is a paper from Pasquale Calabrese, who was looking at exactly these things, that at these systems where the entanglement entropy first grows linearly, then it reaches a plateau, and then you see this dip where the entropy decreases. And he has a paper explaining that, and I can look this up and paste it into the chat. I think, I'm not sure if this is correct what I'm saying now, but I think it's a property of integrable models. Where you can,
that would kind of like go in line with what Nicole said, right? Like with the revivals, now that I look at it, it kind of looks like that. Like it's just like translational,
right?
A translation in time.
Mm-hmm. Yeah.
Hi, Rick. I'm an experimentalist working on Misha Lukin's Rydberg atom array experiment.
Okay.
And so, yeah, and I think one of our students actually really appreciates your previous work on SLMs. So.
Okay.
My question is, looking at entanglement growth across the quantum phase transition is, as you've said, is a interesting way to apply this to a quantum many-body system. What other kinds of experiments and data sets would you love to get your hands on to do this analysis with?
Ooh, that's a nice question. What data sets would I like? Actually, so maybe this is again something for Christian, who's been looking at negativities in Rydberg systems. So just to put it on your.
Yes, I mean this is not directly related. Maybe let me answer it first differently, and then just say something about what you just mentioned, Rick. One thing about this entanglement Hamiltonian tomography is that that in contrast to standard quantum state tomography, like this projected least squares or things like that, we don't have to measure in that many different bases. So if you actually, we found that for ground states, if you apply this entanglement Hamiltonian tomography for ground states, a single basis is enough. Yeah, so you just choose one set of random unitaries and you just sample your product states in this single basis, and you fit your entanglement Hamiltonian to this data set. And it turns out that in this case, you're able to extract a complete density matrix. And if you ask, how is this possible that a single basis can really be enough? And this is because of the Ansatz, because you make this Ansatz for the entanglement Hamiltonian, and this Ansatz sort of already fixes the off-diagonal terms. So a single basis could be enough. And if I think about Rydberg experiments, for instance, what you guys do in Harvard, it might be not obvious to measure in an arbitrary amount of bases. Let's say, if you think about this Rydberg constraint, please correct me if I'm saying wrong things here, but if you have this Rydberg constraint, it's, for instance, not so easy to measure all the atoms in the X spaces, for instance, all the atoms in the superposition between ground and Rydberg states.
That's right.
Right. So this is exactly something where this can be useful.
Yeah, this is actually a good point. Like, we talked a few times already to the guys in Paris, like all the times they were asking us, what can we do with your stuff? And every time we needed local rotations, for instance, and this is something they don't have and still don't have. And every time, that's why all these cross-platform verification protocols, for instance, that I mentioned, that we couldn't really do them there. But actually, for some of these things, like this Bisognano-Wichmann situation, it is, as Christian says, something we found. You only need one basis, or maybe 2 or 3 is already enough. So if you can measure everything, at least, so you don't need local rotation. So at least if I can measure everything in Z and everything in X, that might be enough. And for simple cases like here, this Bisognano-Wichmann, everything in Z is already enough.
Okay, great, thanks.
Are there more questions? Well, if not, I mean, I think we've had a very nice discussion, also on the experimental side. Thanks again, Rick, and also Christian, for joining in. That was the last talk of this ITAMP seminar series for this semester, and it will